Hello and welcome to this incisor tutorial. In this tutorial, we'll be walking through a step-by-step example in which we modify the incisor slot template project to give the reels a curved stepper reel appearance. By the end, you'll have two different techniques for creating curved reels, and then we'll take a deeper look at how the shader-based version is built under the hood. It should be noted that some of the features in this tutorial require an Incisor Pro subscription or higher. Section 1. Curved Reels without EffectNodes. We'll start by downloading a copy of the Incisor slot template. For this example, we'll be using TypeScript. Let's rename the project to reflect that it's a version of the slot template with curved reels. We're going to be exploring two quick ways of giving slot reels a curved appearance, and both of them make use of Incisor's perspective camera, which provides an easy way to create the bulged look that best represents 3D curvature. To do this, we can change the main camera from orthographic to perspective in the project settings pop-up. Now we can save and reload. You'll notice that the defaults for this perspective camera make it so that the main content of the slot template is a bit too zoomed. To fix this, we can play with the core view angles in the object panel to get an idea of what the values should be, and then we can change those values permanently by adding a line to the project main in code. Now let's recompile the TypeScript to see the permanent change in the live view. Now we'll show a very quick and easy way to give these slot reels a curved look, and it will only take a few lines of code. Since we want to give the appearance that the symbols on this reel are arcing toward the viewer as they travel from top to bottom, we will open the slot reel symbol TypeScript file and edit the update symbol position function. When implemented in the slot reel symbol class, the update symbol position function is automatically called by the owning slot reel class every time it updates the symbol position value of each slot reel symbol. This function can then be used to interpret the new symbol position value, which operates in a range where the first visible symbol's value is 0, the second is 1, the third is 2, etc. So, to change the path of the symbol, we can simply add two lines to the function. The first line gives each symbol a rotation that gradually changes as the symbol position increases. And the second line gives each symbol an adjusted Z position value that also steadily arcs toward the camera and then away from the camera as the symbol position increases. Here we're using a sine function to approximate the curve of the reel as a quick example, but it should be noted that it's only a rough approximation. Any mathematical expressions can be used here to dictate the rotation and location of the symbols according to their symbol position value. Now we can recompile the TypeScript and see the effect. Notice the bulged appearance. This is because the symbols are now moving closer to the camera, which causes them to appear larger when viewed through a perspective camera. Because we're actually changing the Z position of each symbol in 3D space, the perspective camera naturally turns that into a convincing bulged effect without us needing to write any shader code yet. With this new symbol path, our reel masks are cutting off at the sides. We can fix this by scaling up the reel mask graphic objects in the game layout construct. We just go to each reel mask graphic and increase the X scale value. While this way of giving the reels a curved appearance is really quick and easy, if we look closely, we can see that this method leaves each symbol looking like a flat panel instead of a completely curved surface. This method also doesn't mimic any of the effects of how light interacts with a curved surface. So next, we'll upgrade to an effect node-based approach that actually deforms the geometry and adds curved shading. Section 2. Curved Reels with a custom effect node. In this section, we'll use a custom effect node to get a more realistic curved reel with shading, without worrying yet about how the shader itself is written. We'll treat the effect node as a higher-level tool, and then do a deeper shader dive in the next section. First, we'll comment out the symbol path altering lines that we added to the update symbol position function, and when we recompile the TypeScript, we can see the reels are flat again. Next, we'll use the template library to create a new effect node to achieve the exact look we want. Let's base our new effect node on the Arch effect node in the Incisor template library menu. We can rename it to Curved Reel. We see now that this has added a new code asset file to our project's assets directory. Let's open it and have a look. This particular code asset defines an effect node and the associated effect controller. Effect nodes are modular visual effects that can be applied to any graphic object in any combination and order. When an object has more than one effect node, Incisor automatically builds a bespoke shader for that object based on the combination of effect nodes that a given object has. Each effect node can have effect controllers, which are just the properties that enable us to manipulate the given effect. You can think of effect controllers as the knobs and sliders for that effect. Fundamentally, effect nodes are applied directly to the materials of graphic objects, and the materials will be given the companion effect controllers. One of the nice things about the way that this works in Incisor is that effect controllers can be adjusted on any scene object, and those adjustments will automatically apply to all of that scene object's descendants. This makes adjusting the visual effects of groups of objects really easy. For example, you'll see that as a default, all of the materials in Incisor projects have the Color Multiply effect node and the associated effect controller. We can adjust the effect controller on every material individually, but we can also go to any point further up in the hierarchy and adjust the values for groups of objects with a single slider. This can be done either in code or in the graphical user interface. For now, we'll quickly modify these definitions from their original Arch functionality and change them to produce the curved reel effect we're after. We'll do a deeper dive on how to do this later in the tutorial. Now that we have our Reel Curve Effect Node asset in the project, we can wire it into the slot template without worrying about its inner workings just yet. In the Incisor slot template, the effect nodes for the symbol objects are explicitly set in the start callback of the slot_reel symbol class. If we add the Reel Curve Effect node here, we'll see the change when we recompile the TypeScript and rerun our project. Once we do that, you'll notice that each symbol is positioned and shaded as if it were in the topmost reel position. This is because the progress component of our Reel Curve Effect controller needs to be updated according to the symbol position value of each symbol. To do that, we can simply add a line to the Update Symbol Position callback. Notice that our custom new effect controller automatically appears in autocomplete when we dot our way into the slot reel symbol object. This is because Incisor's dynamic autocomplete detects definitions and adds them to the Incisor API reference file in the project utilities. Once we have the progress component being updated, we should be able to see our reels curving nicely according to our new effect node. Notice that the effect node is now evenly deforming the symbols on the desired curve, and they now have shading to help reinforce the curved reel effect. We now also see our effect controller supervisors on the slot reel symbol materials, as well as all of their ancestors. Because of Incisor's inheritance scheme, all of the effect controller values for all of the symbols can be adjusted from a single hierarchy owner. Since the Reel Curve Effect node adjusts the actual positions of the vertices in our symbols, the main camera, which is now a perspective camera, will display this vertex deformation in full perspective 3D. To push the curved stepper reel look even further, we can add a symbol background image to the project and tell the slot reel symbol to add it as a child. We'll make a new layer between the reels and the reel background and add a line to put the new graphic object on that layer. Recompile the TypeScript and see the result. This new background image is a nice touch when it comes to recreating the look of the reels in a physical stepper, but when we look more closely, we can still see evidence that the symbol background image is made of rectangular panels. This is because our symbol background image is a simple rectangle, and therefore its geometry only has 4 vertices, 1 in each corner. Remember that our Reel Curve Effect node is literally moving each vertex along a curved path in 3D. With only 4 vertices, we're essentially bending just a single flat quad, so it still looks like a panel. To make the curve look smooth, we need more vertices for the effect to grab and bend along the reel. So while our effect node is working as designed by putting all of the vertices on a perfectly curved path, we will need to increase the number of vertices in the symbol background to avoid the appearance that the reel is made of flat panels. Incisor can do that too. To modify the geometry of the symbol background image, we can use the nc.editGeometry function. Since this function requires the provided geometry to be loaded, we can either asynchronously await its execution using the await keyword, or we can provide a callback that will be called when the geometry loads. The call to nc.editGeometry returns a geometry editor object that allows us to make changes to the geometry in question. We'll use the newGrid function, which makes a grid geometry in which we can pick the width, height, and number of horizontal and vertical segments. For width and height, we can just enter the dimensions of the source image, and since the curvature affects the symbol's positioning along the vertical axis, we'll be sure to include plenty of extra vertical segments in the new geometry. The more segments we add along that axis, the smoother the visible curve will be once the real curve effect node deforms it. Now we just need to call commit changes on our geometry editor, and then we can recompile the TypeScript. We can see that our symbol backgrounds are now smoothly curved by the real curve effect node, and it no longer looks like the symbol backgrounds are made of flat panels. To show off our new real curvature in full perspective 3D, we can also add some motion to the rotation property on the reels container to keep our reels moving. At this point, we've used the real curve effect node as a tool. We created it from the template library, wired it into our symbols and backgrounds, and adjusted geometry to make the curve look smooth. In the final section, we'll look under the hood at how an effect node like this actually works, and how the shader code is structured. Section 3. Deep dive on effect nodes, shaders, and the real curve implementation. In this last section, we'll step back and look more closely at how effect nodes work in the context of GLSL shaders, and how this particular real curve effect node was built. If terms like uniform and varying are new to you, you can think of them like this. A vertex shader moves the corners, or vertices, of your geometry in 3D. A fragment shader decides the color of the pixels on the surface. Uniforms are the adjustable inputs to those shaders. In Incisor, these are exposed as effect controllers. Varyings are values passed from the vertex stage to the fragment stage for each pixel. You don't have to be a GLSL expert to follow along, but this should help the structure make sense. Let's look more closely at the definition of our effect controller, which takes place in the nc.defineEffectController function call. First, we supply the name of the effect controller. When an effect node has a single effect controller, the incisor convention is that the effect controller is camel case and the effect node is title case. Next, we have to pick a type for the effect controller. In this case, we're going to use a vector 4 for this effect controller, where the individual components each control a different aspect of the associated effect node. Next, we give the components descriptive names. For this particular real curve example, our effect controller will allow control of the progress along the curve, the depth of the curve, a location along the curve for a bright, shiny reflection, and the brightness of that shiny reflection. Next, we supply the default values for each of the components. This parameter here determines how the effect controller values mix together as they are passed from parent to child in the inheritance discussed earlier. This parameter lists the likely ranges of the component values and helps inform the slider sensitivity of the supervisors in Incisor's graphical user interface. Larger ranges here make the sliders more reactive. This parameter is a description of the effect controller in general. This description will appear in tooltips in the graphical user interface as well as autocomplete whenever you dot into this property within an owning scene object. This parameter is for descriptions of the individual components. So now that we have our effect controller defined, we can have a closer look at the definition of our effect node, which takes place in this call to nc.defineEffectNode. The first parameter of this function is the name of the effect node. The next 4 parameters are where we include the actual GLSL shader code for this effect node. This tutorial will not go into great depth on the subject of writing the actual content of the shader code, but in general, shaders are a means to enable the graphics card to calculate or modify the positions of vertices within geometry and the color of fragments, which is another name for the pixels drawn on the surfaces of geometry. As such, shaders are broken into two parts, vertex and fragment. So this second parameter is where you put the shader code that supports the vertex portion of this particular effect node. In other words, this is where you put declarations of the varying and uniform variables that will be used within the vertex portion of the shader code. You can also use this portion to define functions that can be called from within the main vertex body. Notice that the supplied vertex support parameter can be either a string or an array of strings. Supplying the vertex support as an array of strings, as we've done here, allows you to break statements up, and in the event that multiple effect nodes make use of the same supporting statements, INCISOR will cull the duplicate statements to avoid shader errors. The third parameter is where we put the portion of the vertex shader body code for this effect node. You'll notice that this example, and many of the other examples included in the INCISOR template library, usually end with a statement involving the vertex vec3 variable. This is because the primary job of the vertex node is to calculate or alter the positions of vertices. One important thing to remember when building your own effect nodes is that each of these code blocks will be compiled together with the code blocks from other effect nodes, so you'll want to be sure you are specific with the names of your variables and avoid using the same variable name within two effect nodes that may be used together, as this will cause shader errors. The next two parameters are similar to the last two, only these two define the fragment portion of the shader code in this effect node. So the fourth parameter is for the shader code that supports the fragment portion of the effect node, and the fifth is for the shader code for the main body of the fragment portion of the effect node. It should be noted that many effect nodes include only vertex code or only fragment code, and to do so, you simply supply empty quotes for the appropriate parameters. Finally, we look at this sixth parameter, which is where we list the effect controllers that are going to be associated with this effect node. In this case, we supply a list containing the effect controller we've defined above. While there are more optional parameters in the define effect node function, they are generally for more advanced uses, and these 6 are all we'll need at the moment. You can see more examples of how effect nodes and effect controllers are built from within the INCISOR template library. Adding these examples to a project, checking out the code, and playing with modifications is one of the best ways to familiarize yourself with making new shader-based effect nodes. If you are using AI to help you, remember that INCISOR publishes its entire knowledge base in an AI-friendly format at INCISORDev.com. And that concludes this Curved Slot Reels tutorial. A link to the project in this tutorial is in the description below. Downloading this project is a great way to explore the concepts we've reviewed. You can find more tutorials at INCISORDev.com, and if you have any questions, feel free to ask them on Stack Overflow or on the INCISOR subreddit. Enjoy creating with INCISOR.